In the previous lecture, number 6, we developed an understanding of how natural selection works. Now in lecture 7, this one, it's time to add mutation to the mix and consider the balance between mutation, introducing new genetic variation into a population, and selection, tending to sort it out. We expect most new mutations to be harmful. Why is that? Many random changes, as we've seen, will actually destroy a gene or degrade its product or seriously mess up its regulation. It's easy to understand why those mutations would be bad for fitness. And very few mutations will actually improve a gene's performance because it has already been polished by often millions, many millions of years of natural selection to do its job as well as possible. And these simple expectations are very strongly confirmed by the mutation accumulation experiments like that of Larissa Vassilieva and her colleagues, which we reviewed before. And here's the key figure from that study. So a very key question is, in a large outbreeding population such as ours, how common are deleterious mutations expected to be at equilibrium? That's what we're going to focus on, is the equilibrium between mutation, introducing new mutations, most of which are some degree of bad, and selection, which is tending to favor improved performance and fitness. Now, we had a clicker question on this last year. People were given the choices very rare, modestly rare, common if they're only slightly harmful, common even if they're very harmful but recessive. You might think about which of those you would click. This is actually a tricky question. It's not as simple as you might imagine, but we'll move on now to focus on the slowness, or if you like, weakness of mutation as an evolutionary force. And that's a result of the fact that mutation rates are, as we might expect, amazingly low. Here are Heron and Freeman's mouse life cycle diagram with an initial allele frequency of 90% of the big A gene, so 10% of little a. Here are the Hardy-Weinberg genotype frequencies. They are unchanged by development and maturation, and then the adults make new gametes to make the next generation. And we have a mutation rate here of 1 mistake per 10,000 meiotic events or gamete production events. That's 10 to the minus 4 per generation. And so that would be written as M or mu. We'll use the Greek lowercase mu, which is a common symbol for the mutation rate, 10 to the minus 4. And I just want to emphasize that that's actually a very high mutation rate. It might it does apply per gene in us in a few cases, apparently, but no nucleotide level mutation rate in us would be anywhere near that high. And yet, what does it do to our allele frequency of 0.9 of big A? It reduces it to 0.89991 and increases the frequency of little a to 0.10009. Okay, a very small change per generation. Only RNA viruses, which have the highest known mutation rates, and the coronaviruses are in that category, have mutation rates as high as 10 to the minus 4th substitutions per nucleotide per cell generation. In this recent survey by Peck and Loring, noted on the right, estimates of the per cell generation mutation rate are plotted on the x-axis, and the resulting evolutionary rate as substitutions per nucleotide site per year are given on the y-axis. Those are much higher, of course, because there can be many virus life cycles per year. So here's the cloud of RNA viruses, which all but one of the species in this figure are. There's one DNA virus, herpes simplex virus, which has a vastly lower mutation rate because its genome is DNA, which tends to mutate at a much lower rate. All right, so the mutation rate is a weak or slow force, but selection can also be slow and weak, especially if the mutation is recessive. And so the interesting question for us is, how do these two opposing processes, both of them very weak or slow, interact? To find out, let's go back and review that marginal fitness concept that we developed last time. Under random mating, P, the allele frequency of the, let's call it the wild type normal form of the allele of the gene, P is the probability that any allele will find itself in a genotype with another copy of A1, and Q, 1 minus P, is therefore the chance that any gene at all is with an A2, the mutant form. That's true because of the random mating assumption. Thus, an A1 allele will be in an individual with a fitness of W11 with probability P, and it will have fitness W12 if it's with the mutant allele, and it'll experience that with probability Q by definition. So its marginal fitness will be P times W11 plus Q times W12. That's just an idea we developed in the previous lecture. So in the same way, the A2 allele, the mutant, will have fitness W12 with the probability it's in a heterozygote, which is P, and it'll have the homozygous mutant fitness W22 with probability Q, given that it's an A2 allele. So its marginal fitness will be, as we saw before, P times W12 plus Q times W22. So by how much does selection then reduce the frequency of allele A2, which we're assuming to be harmful, in one generation? Let Q be the frequency of the recessive deleterious A2 as usual, and the genotypic fitnesses, because of our assumption that A2 is fully recessive in its effects, the genotypic fitnesses will be 1 for both the A1 homozygote and the heterozygote, so W11 and W12 are equal to 1, and the homozygous mutant fitness will be something less than 1, perhaps, as we'll see, a lot less than 1. The marginal fitness of the normal A1 allele will be 1 by our assumption that the effects of A2 are recessive, because both of the genotypes in which it occurs have full fitness. The marginal fitness of A2, however, is more interesting. This is where the action is. So W2 is going to be, by definition, P times W12 plus Q times W22, but because we've assumed W12, the heterozygote fitness, is 1, this is just P plus Q times W22. But Q is close to 0 in all the cases we're interested in, because we're considering the A2 allele to be deleterious, that is, harmful, to have a fitness less than 1 in the homozygote. So that keeps Q close to 0. So P is therefore close to 1, and W2 will also be close to 1. That's the marginal fitness, not necessarily the homozygous fitness W22, but the marginal fitness of the A2 allele is also going to be close to 1 because mostly it occurs in heterozygotes. So the mean fitness of the whole population, PW1 plus QW2, is also going to be so close to 1 that we can just disregard it. So that simplifies the selection equation by eliminating the W, or if you like, W bar, the population mean fitness, from the denominator of that ratio. And so to a very good approximation, in this situation, Q prime, the allele frequency next generation of the mutant A2 allele, is going to be its frequency this generation, Q, just times W2. We don't need to have a W bar downstairs. Okay, and therefore the allele frequency change in a single generation, delta Q, is just going to be Q prime minus Q by definition of the change. And that's therefore going to be QW2 minus Q, which is just Q times W2 minus 1, which is to say the difference between the marginal fitness of the A2 allele and 1 as a negative number, because W2 is, by assumption, something less than 1. Okay, so delta Q will, under the force of selection, will be negative, selections tending to eliminate the mutant allele. But mutation is tending to increase its frequency because most of the alleles in the population are A1, and they're the ones that are mutating to the A2 form. So the slow change in allele frequency caused by selection is negative. The slow change caused by mutation from A1 to A2 is positive, and it is, to a good approximation, just the mutation rate, because by assumption Q is close to 0, so most of the mutation is from A1 to A2. The frequency of A1 is close to 1, so P times mu is close enough just to mu, and so at equilibrium these two have to be equal. That's what we mean by equilibrium. The decrease due to selection plus the increase due to mutation must balance out to be 0, which is to say they are equal in size and opposite in sign. And so after a wee bit of algebra, we get the equilibrium frequency of A2, which is just the square root of the mutation rate to A2 mu divided by this thing S, which is just 1 minus W22. That is the fitness loss suffered by the A2 homozygotes. In general, the notation S comes from the concept of the selection coefficient. So it's the first letter of selection, which is just a proportional loss of fitness in most cases. In any event, in words, our result is that the equilibrium frequency of a purely deleterious recessive allele is just the square root of the ratio of the mutation rate and the strength of selection against the affected homozygotes. Deleterious mutation rates can be high. There's a much studied gene in our species called TEL-SMN, which causes in the homozygous state a bad condition called spinal muscular atrophy. A study was done of patients that were found to carry new mutations that were not present in either of their parents, and that implied 7 of these 340 patients had these new mutation, and so that implied that the mutation rate in the parents must have been around 1 times 10 to the minus 4. This is explained in Heron and Freeman on page 221. The selection coefficient for homozygotes is estimated to be very high, around 0.9, that is to say few affected individuals, that is few homozygotes, ever end up reproducing. And so the predicted allele frequency at the mutation selection equilibrium, given our little model on the previous slide, should be around 0.0001. That's this very high mutation rate of 10 to the minus fourth, divided by the selection coefficient, 0.9, which is for all practical purposes 1. Take the square root of that, which is just like the square root of the mutation rate, which would be 1%. And indeed, in Caucasian populations, roughly 1 in 10,000 infants is affected by this condition. That implies, on the outbreeding assumption, that Q squared is 1 in 10,000, 0.0001, which is to say Q would be like 1%, in amazingly good agreement with the mutation rate estimated directly from pedigrees and our simple model of mutation selection equilibrium. But in fact, the equilibrium deleterious allele frequencies are expected to be high even with low mutation rates. Let's go to the opposite end of the per gene spectrum in us and pick a low mutation rate of like 1 in a million per generation per gene, not per nucleotide frequency. So what's the equilibrium frequency of a recessive lethal allele in that case? Well, here's our little equation again, predicting the equilibrium deleterious lethal recessive allele frequency, mu over S. What do you can do that in your head. Actually, this was a clicker question last year. Let's just do it here mentally. Well, the mutation rate, we just gave it its 10 to the minus sixth. S, this thing is, let's just assume, completely lethal in the homozygous state. Okay, so S is 1, so we can just eliminate that. So the equilibrium Q is going to just be the square root of the mutation rate. What's the square root of 10 to the minus sixth? Everybody, you know the answer, right? It's 10 to the minus third, which is to say 1 in 1,000. 1 in 1,000. Okay. What's the frequency of the heterozygous carriers? You know how to do that too. The heterozygotes under outbreeding, under random mating, are in frequency 2pq. All right, Q is close to 0, so P is close to 1. So that's just close to 2Q. So if Q is 10 to the minus third, what's 2Q? It's not any of those numbers. It's 1 in 500. And that's true at any locus subject to mutation to recessive lethal alleles in an outbred population, given complete recessivity of the effects. And that's true at every locus. So imagine how many genetic loci in the genome are there probably capable of mutating to recessive lethal conditions. That is to say, how many genes that we absolutely have to have at least one working copy of to be alive. It's probably a lot of them, which implies, with a little thought, that every one of us is probably the carrier of several such deadly genes in the heterozygous state. All right, let's leave it there, and we'll come back in the next segment to look at some actual data on deleterious mutation frequencies in us.